Excellent. So, Gary, thank you very much for coming to talk to the DRACHMA network, the drone research for advancing community healthcare and medicines access. And hopefully you'll become part of our community in subsequent meetings. And I think you're going to be talking to us about, well, safe landing and precision landing when GPS systems are denied. So the floor's yours.
Yeah, thank you. So I'll just do a quick introduction. So my name is Gary Gaz. I'm the product director for our nav systems business at GE Aviation. And part of that portfolio includes what I'm going to talk to you about today. But the rest of my portfolio is my big product is flight management systems, which we put on all types of aircraft, and as well doing all kinds of navigation solutions, which is where this falls into, and which also includes other inertial type products, and as well as things that we also look at that aid in GPS denied environments. So we have quite a big portfolio. This is a small new, I would say new, but it's a lower TRL product, technology readiness level. But we have done some testing with it, some flight testing. So we'll talk more about that. And just by way of background, I've been in the avionics business and in the industry for about somewhere north of 25 years. I've been with GE Aviation for about 13 of those years, and the rest was with my prior company. And I've been in this role for a few years now. So with that, I will switch over to my presentation. Share. Are you seeing the full presentation? Just want to check.
Yep, looking fantastic, Gary.
Okay, let's see. Oh, I started at the end. I got to go to the beginning here. Here we go. All right. So the idea of this technology is for a relative navigation system. So irregardless of any other types of signals or ways of navigating, this uses a stationary platform. Well, it could be a moving platform as well. So you can see the ship in the upper middle. But basically a platform that has a transmitter, a laser transmitter on the platform. That transmitter puts a grid out into space from its location, and on the vehicle. In summary, really, the vehicle has a set of receivers that detect where it is in that laser grid. And so what you're seeing here is just different use cases that we've, in some cases, we've tested and experimented with to ensure its usability and feasibility. And so just for various, go around the horn on the display. The upper left is oil rig platforms, where we've looked at aiding helicopters to land on oil rigs. In the upper middle, on a moving ship at sea, that all the dynamics that come with that, with the motion of the ship, forward motion, the waves, things that make so it's not a stable platform. We've tested it in those environments. We've done it with aerial refueling, where the transmitter is actually hosted on the back of the tanker. And there is actually two sets of sensors on this system. One is on the drogue that comes out of the back of the tanker, and the other is on the aircraft that's being refueled. The urban air mobility use case, having the small VTOL aircraft landing, on top of a building or a vertiport. Even as far as drones being able to be used and even swarmed out of a moving air vehicle for recapture, for example, and then as well, landing a helicopter on top of a hospital. And so these are some of the use cases. I'm sure there are many more that people can be creative and think of with this kind of technology. So what is it? The technology, we call it EOGRS. It stands for Electro-Optical Grid Reference System. And so really, like I said earlier, it's self-contained means of utilizing a navigation solution for takeoff and landing, and it is fully independent of GPS and really any other need for any other signals. It's standalone, could be used as a backup, or it could be used as an aid for other current landing type systems. It is very small and lightweight, low power on the for the on-aircraft components, and we're going to go into the components here later. It's an open and simple aircraft autopilot interface, so we use standard interfaces. We can use CAN bus or Ethernet to talk to any of the other systems on the vehicle. And then we can talk directly into another system like an autopilot or a flight management system. The architecture does minimize cost and complexity on the aircraft. So like I said, it's going to be small, lightweight, and very simple. It is stealthy. So for places where emissions of RF energy is of a concern, or jamming is of a concern, this is light based, so very difficult to spoof or jam. And we have done testing in a DVE in diverse environmental conditions. So weather, darkness, things like that, where we've done some testing, snow, rain, fog, things like that, where we've got some level of confidence in its ability in those conditions. So just nice little picture of the system, and we'll go into some more detail as well. So on the ground side, or the platform side, I should say, the transmitter subsystem is what we use. That consists of an amplifier for the laser, the seed laser with an electronics package, and then a transmitter, a scanner head, which actually creates the grid in space. And so that's what's put on the ground. On the aircraft that's going to be detecting where it is in the grid, you need the receiver subsystem. That consists of the laser grid detectors, and so there would be a minimum of 3 of those laser grid detectors to triangulate where you are in the grid. And then the actual grid detector unit, which is a small device that pulls in the information from the detectors and translates that so it can be absorbed into a common filter. That common filter is not shown here, but that would be hosted really on any other electronic system that's on the vehicle, or we have one as well that we can use. It's small from a avionics perspective, but it's overkill from a compute power and size and weight perspective, because if all you're going to do is host the common filter in that, I'm sure there's other electronics on the vehicle that we could do that with. Or you can even use that system to host other applications as well. So we can go either way. And then that would interface with the flight control computer and the flight controls. And so really just kind of a little bit more elaboration on how it works. So the aircraft in the upper right, when you're talking about an approach, the initial approach into the location that you're coming into. So we think typically with urban air mobility, these aircraft, VTOLs are flying in fixed wing mode, typically flying towards its destination. It would use traditional navigational means to do that. When it gets within the range of the transmitter, and that would be within where your final approach fix is, that's when you would then transition to the relative navigation system and be able to determine where you are in that grid. And so what that requires is the transmitter and detectors, obviously, like we just talked about. There is another piece here, and that is the data link. The data link is colored differently in italics because it's not necessarily required for a system, especially a system that's landing on a stationary platform. Typically, when you're on that platform, where that platform is. You can put that in a navigational database. It's not required to understand what's going on at the transmitter side via the data link, and that's the purpose of the data link. On a moving platform like a ship at sea or an aircraft, in a refueling situation or a recapture situation, the data link gives the information of exactly where the transmitter knows it is. And so when the receiver on the receiving vehicle is trying to determine where it is in the grid, it also has to know where the transmitter is starting from. So there's that point in space that it has to figure out. And so with the stationary ground, top of a vertiport, for example, there are no, it's not a question, you know where that location is, but obviously on the moving vehicle, you have to constantly communicate back to keep the information on aircraft with the moving platform in sync, and that's what the data link does. And so there's another use case here with the refueling example where we've done testing with the drogue. So the drogue itself, you can see in the picture here, it's got the inside the grid, and so the transmitter is on the tail of the aircraft, and it's pointing down and away from the aircraft. The drogue that comes out behind will fall in within that grid, and the detectors on the drogue determine where in the grid it is. And so that's where the data link is also helping this in this use case. It's telling the receiver on the receiver vehicle, hey, here's your transmitter, here's where the drogue is in space, because that's moving around, right? And this way the receiver can guide itself into that drogue. And so we've actually tested that in a flight test. And so I get a lot of questions about range on this. So range is not a static piece of information I can share. And that's because it really depends on the installation of the detectors on the vehicle that you're going to fly it on. So the spacing of those detectors. So like I said, we have 3 of those at minimum, and you could do more, which would help with the accuracy. It won't help with necessarily with the range as much, but it will help with the accuracy. And the reliability, I should say. So when you're looking at about a 3-foot separation on a vehicle of the detectors, you're looking at 50 feet. You're at about at 500 feet. I was going back. 500 feet. You're looking at an accuracy of about 50 feet. So your uncertainty is about you're within 50 feet. But when you're all the way at the other end of the spectrum, where you've got 20 feet separation, so if you're on a large vehicle, then you can get kind of pretty accurate. You're kind of down into less than 10 feet at 500 feet. So at 500 feet distance, your accuracy is at 10 feet. And then obviously that accuracy wanes as you get further away, because the grid spacing, as you move further away from the transmitter, become larger. So the squares of the grid are much wider. So the accuracy cannot be as accurate as you are when you're close up to the transmitter. So we've done testing, and we've actually done testing where in simulation we can get to 3,000 feet. We actually haven't tested in actual flight tests at that range. We have tested at about 1,500 feet, and that's been very strong. And so some of the simulations we've done, we can get up to 3,000 feet. And then the accuracy too, one of the nice things about this system is when you're far away from your destination, the accuracy isn't as important. Obviously, if you're traversing through an urban environment and your accuracy is, up in the 300 feet range, at 2,500 feet, for example, you could be, that could be buildings, right? So there is an understanding there that there is that function of that where you place the grid on an approach into the landing location needs to understand the accuracy at distance, so that the vehicle isn't totally reliant of an exact precision at a great distance, like 2,000 feet. The precision really comes in as you approach the transmitter, and when you get close to that transmitter, you're going to get the accuracy down. You can see your accuracy is in less than a meter in all cases, no matter what the spacing is on the vehicle, as you get close to the landing zone. So you're going to get pinpoint accuracy as you get within a couple of feet and that final landing spot of the vehicle. So moving on to the components of the system. So like I said, there's 2 pieces. We'll get into a little more detail on both of these. The transmitter side, like I said earlier, so you've got the seed laser. So there's some close-up pictures of the current setup. The seed laser on the left That's generating the laser, the amplifier, which creates enough power for it to be used by the scanner, because the scanner is basically taking that laser and splitting it up, right, into this grid that it projects, and that projects, each line is being projected at 20 hertz rate, and it also is embedding in the light a reference number in the light path. So when you're trying to figure out where you are on the grid, that's how the detectors know. It's detecting the wavelength in the light that's coming off of that particular line in the grid, and so it can determine which line it's looking at in that grid, therefore determining where it is in the grid. And so again, on the receiver side, the detectors, and we standardly go with 3 detectors. That's you need that turns that photon imagery back into digital data. Then that data is again, it's that precise measurement, azimuth and elevation of those of where those detectors are relative to the transmitter. So each detector can detect its own location in the grid. Another reason to have 3 is, especially at distance, you may not always be detecting, all 3 detectors may not always be seeing a line in the grid at the same time. So there could be periods, small periods, less than seconds in when you're in that grid where you could potentially not be seeing that line. So, but the detection is happening at a fast enough rate that as the vehicle moves through the grid, it's always at least one of the detectors is picking up one of the lines. And the grid detector unit, the GDU, that collects all the data from the detectors and conglomerates that and passes that on to the common filter. And like I said, we have a electronics unit we call the M100 that we host the common filter in for our testing, but for in service, that would be something that you would look at as is that a box that would be necessary for the platform, where you could host other applications in it, or which we've done, or you can go the other way and say, okay, we'll just put the common filter in some other electronics unit, or even include it if there's another common filter on vehicle that could do the same function. We could help augment that with how we build our common filter. So just a little bit of history on these. The transmitter has gone through a couple generations already. So the first generation was a 980 nanometer laser, 600 watt laser module. That range was not the distance that we have today. So the 980 was only get up to about 300 feet. That is the one we did testing on a tanker with a vehicle flying behind it with NavAir. And then after we went down that road, we introduced a 1550 nanometer laser that's only 3.5 watts. This really gives us a lot more capability in diverse environmental conditions, provides more eye safe operation within like 3 feet. So you can be 3 feet or further away and it's eye safe, looking right at it, of course. We did adjust it to be have better gain on the receivers. We increased the range to about 3,000 feet, and we've reduced the overall scanner size. And so the picture at the bottom of that is the current setup in the lab. So you can see on the, see here's the grid transmitter. So this is the scanner head. You can see the seed laser is back there, and then the amplifier is in the case. And then we have some control switches and things that we can use to turn things on and off and enhance things and adjust gains and things like that. The next generation, which we haven't really done much work on, we did a little bit of research on this already, so we kind of know the art of the possible, and where we integrate a photonics approach, really combine all 3 of these major components into one single system. So it'd be something that's more scalable, and then increase the range. We think we can get that range up to about 5,000 feet, and then of course, further reduction of the onboard component if you were to put this on a moving platform like a tanker or even a helicopter that could be retrieving drones, for example. So that would be the one of the purposes there. And then of course it could be also man portable for field operations in areas that doesn't have other landing system kind of capabilities. So you could potentially bring that out into the field as well. On the receiver side, So we've got really 2 generations on this, really not necessarily a plan for a third at this point. The first generation was kind of a large, clunky box. It had MEMS IMU in it, inertial reference unit. The FPGA was there that gathered all the raw detector data. Then we had a microprocessor that hosted the common filter and processed the pose and the positional velocity. And those detectors had a 60-degree field of view. So the detectors themselves are the same. So we don't have a new generation detectors. Those detectors work just fine. So we're using those same detectors. The second generation, though, you can see in the upper left corner of this picture, this is a smaller version of this box. This box is probably about 8 inches cubed, about, give or take. Sorry, 8 inches on a side, I should say. This box is about, right now, it's about 2 inches by 3 inches by about 6 inches. Really, that's a prototype 3D printed box with some heat sinks to get the heat out of it. Ideally, when we package it for a production unit, that would really get down to about the size of a deck of cards. So that box would become really small. And that's the target size there, the 2.5 by 4.5 by 1, with a target weight of 8 ounces and 4 watts. So that's kind of in the prototype phase right now. So that's the first prototype. The circuitry inside, the FPGA and the circuit card that's in there, that is small enough to fit in this envelope that I'm presenting here for the future. And then here's just a picture of the separation. So this rig that you see here has the 3 detector units on it. This is about 2 feet wide. That's the tape measure is showing. And we put this on a drone today with that box to do testing. So that this is actually the setup we stick on top of a drone to do the testing with the laser on the ground. And then just kind of my get off the stage slide. The UGRS is a technology can provide really auto land, refueling, man-to-man teaming, and I'm sure so much more that are beyond my creative means. So that's the presentation. That's the long and short of it. I guess if there's any questions, I'd be open to taking those.
Gary, that was tremendous. Just enough of the technology just to whet our appetites. That was really good. Thank you for that.
Yeah.
So, do we have any questions? I mean, I've got a fairly obvious one to start off with. You mentioned you're actually testing on drones, and you've got about a 2 feet separation between your detectors. So, what kind of what kind of size of drone do you think could operate your system successfully?
So we tested on a small drone right now. I'd say it's probably gosh, I mean, it's probably no wider than that rig that I just showed. So that it's about 2 feet wide. It's a 6 prop drone, the one we test on.
Okay,
So
right.
it's very small. I mean, it's a very small drone. You know, I mean, you probably go smaller based on, you know, that drone was picked for that first generation. If I scroll back a slide here, that drone was picked so we could fit this box on that drone. And that box is, like I said, it's relatively large compared to what we were shooting for. So this box right here, actually, if I scroll up a slide or two, let me see, where was that? So this M100 box, this box is slightly bigger than this current box right here. So this box here, I've flown this box on a drone, on just a regular small quadcopter drone that we've built. I don't know if you guys familiar with drones, the Taro.
Okay, I'm with you.
Taro Sport, right? It's a you know, build your own stuff. You know, so we built a number of those, stuck this box on top of it, and flown it. And we've done things like flight controls and flight management in this box. I haven't flown this box yet on that size drone, just because the setup's on that other one. But we could easily put both of these boxes on a Taro right now.
Okay, fantastic. Yeah, because as soon as you try and move medicines around, you know, they're expensive. They've got a big impact, and we want to send them to places where you can't get to. So this technology is perfect for that. Somebody may want to divert something and use it illicitly, so the anti-jamming is very, very good, but also the fact that you've got no other comms available is really good. Oh, Conrad's got a question. Conrad, do you want to unmute and pose your question? Fantastic.
Sure. Yeah, this is quite a sort of low-level question, I guess. It's just about the nature of position error that you get from the device. Does it tend to kind of drift like a GPS device, or is it more like white noise where it sort of gives you a position all over the place within that 50 feet error?
Yeah, it doesn't drift. So because the grid is stable. I mean, you'd have a drift on a moving platform, right? You'd have that natural error that you get, because part of it's because of the moving platform, part of it's because of the delay in the communications, right? So it depends how fast that datacom is. So that lag might provide a slight drift, but on the stable platforms, there really is no drift. The error, the level of uncertainty is really, like I said before, it's kind of driven by the spread of the sensors on board the platform, right? So if you're close together, you may have more of a problem trying to figure out where you are. But if you're, when you have them further apart, more likely to hit more lines, right, in the grid, and that becomes it gives you less uncertainty. So it really becomes a question of uncertainty.
GPS device gives you a reasonably accurate position. It doesn't move around so much. It's just a sort of bubble of uncertainty which you can sort of feed into a filter, which will
so I'll just hold the
I'm getting some sorry, I'm getting a little bit of feedback from someone else.
Hello, I think somebody's got their microphone open and is taking a phone call as we speak. I don't want to dip into your personal arrangements, but we can all hear it.
Exploring opportunities. So let's see what they've come up with.
I think it's Mike. Mike, you
I just put him on mute.
Mike's all red-faced now. Thank you, Mike. It's easily done. Carry on, guys.
Sorry, Conrad.
The reason I had the question is really from a control perspective. It's when your position is quite unstable, it can make it difficult for the aircraft to actually maneuver. And what you really, uncertain is fine, but as long as it's kind of smooth and can be handled, you don't want the drone sort of flying all over the place.
Well, and typically, what we see is, you're in this approach, right? So you're reducing speed, right? You're coming in for your final approach at this distance, and so the testing we've done, you see, we do it, slowly. So we're not kind of coming in for this fast approach. It's not a fixed wing approach, right? We're not advising these for fixed wing aircraft, really. I mean, we haven't tested it in the fixed wing mode. We've tested it with rotorcraft style or VTOL style vehicles. I think VTOL style, where you're coming in a fixed wing mode on approach and then transitioning to a lateral mode, vertical mode. That works, but if you're going to come in a full fixed wing landing approach, I could see where the uncertainty might cause some fits and starts in the controls on the vehicle.
Stuff like that. Yeah, exactly. We had a similar thing. We had to use computer vision for a homing system, and it does a similar thing. It gives you a detection here and then a detection over there, and then you need a lot of part software to sort of handle that without violently moving around too much.
Well, and that's what this grid detector unit really does. It stabilizes the information that's coming into the common filter, so that it's reducing that level of uncertainty. So it is trying to provide more of a fixed position. So it's understanding kind of where it is in the grid. It understands where those three detectors are, and so if the right detector picks up a location, and then the next ping comes from the left detector, right? It knows the spread of those detectors, right? It understands the spread of the grid at the distance it's at from the transmitter. So it has all those algorithms inside that little box. And so that box is figuring out, so it's not providing this, okay, well, 1 minute I was 50 feet this way, the next minute I was 20 feet that way. And it really provides more of a smooth transition. So the information coming into the controls is not choppy like that.
Yeah. Presumably, I mean, within that algorithm, presumably there are some sort of models in there that kind of try to describe the nature of the problem.
You mean the problem we're just talking about?
Yeah.
Yeah, so it does. And I'd have to get my chief engineer on to talk more about the details of this. We're getting a little bit beyond my depth, but yeah, the algorithms themselves are all assuming certain information it knows about how the transmitter and again, there's assumptions it makes based on distance you're at from the location that the transmitter's at and where it
Yeah.
thinks you're at, right, in that grid. So now those, the data link, without the data link, right, that it, like I use the word assumption, liberally. It is truly an assumption, right, based on what it knows about what it's detected so far in the grid, right? With the data link, it solidifies that 100%, right? So now you have, the information of where the transmitter is and how far away you are from that transmitter. So that information becomes more solid as
Yeah.
with the link. Yep.
I see what you mean. Yeah, I mean, a system like that, I guess, needs quite a bit of calibration. There'll be a lot of sort of fudge factors, parameters in there which you need to tune and get right for the particular setup that you have. The reason I was
Yep.
sort of digging on that is because this is something that we have quite a lot in robotics, really. And what we do at Flarebright is we essentially attack these problems with machine learning. So we use machine learning to kind of figure out what these magic parameters should be.
Yeah. And yeah, so that's a good point. So we're still at that point where we believe that the calibration would need to be done on a final production system, but it's not a calibration that has to be done on every system that gets produced, right? So once you have a system and it's configured and it's within certain tolerances for the production units, you can then you don't have to go and do calibration on every single system that walks out the door, right? You can provide that information and then I think one of the things that obviously we haven't learned yet because we don't have this system in production would be over time, right? Is there recalibrations that you'd have to do in the field? We don't know that answer yet, right? So that's something that we would have to learn through continued use and through a full product introduction, right? And figuring that out.
And a lot of data gathering as well.
Yeah, that's right. And that's
Yeah.
where machine learning actually can become very interesting in trying to understand that.
Yeah, exactly. Yeah. Cool.
Yep.
Thanks very much. Yeah, it's very
Yeah, no
useful.
problem.
Excellent conversation. Any other questions from the audience? I've got one around safety, which is kind of my big thing. Well,
Yeah.
I'll crack on with that. I grew up as a chemist in the last millennium of all things. It's terrifying how old you get. And we built, well, I didn't build, but colleagues built Raman spectrophotometers, in optical benches. We fired high-powered lasers around labs. Nobody cared about safety. We all lived. But trying to get on your hospital the estates manager to agree to have a laser put on the roof, it's going to be quite tricky. So how safe is your system? I'm sure it's absolutely fine in terms of the power output, but have you had any thoughts about bystanders? Because if you get into the urban thing, you're going to have people close to it.
Well, yeah. So the real safety concern that we always consider and hear about is the actual laser, right? So you don't want to look directly into the laser, right? Well, the laser itself at the 1550 nanometer is safe within 3 feet. So you could stand 3 feet away and look right at it, and you're fine. So the distance, so that really provides a lot of options, right? It's pretty easy to provide, in my opinion, to be able to provide a means to have a safety rig where you can have, you can really make it hard for someone to be within that 3 feet, right? And I think the other thing to think about too is, where, like you said, where do you install it and who's going to be around it, right? So there's also, just like if you go to an airport, right? Not anyone can just walk around, on the tarmac, right? So, so there's a two-pronged approach, right? So when you talk to the FAA, for example, about what is safe and how do we provide safety, there's multiple layers of how you can do that. And so it's not just the product itself all the time, right? It's also the processes, the installation, right, and the personnel that interact with that technology. And so when safety really comes down to all those things, so we think, from a product perspective, we're probably in pretty good shape on the safety side. The last mile, if you will, right? We always say the last mile in the aircraft world. that last mile, to close the gap on anything that would still be of a concern, in my opinion, would be installation and then personnel, right? So, how do you install it? How do you ensure people don't, come within that 3 feet or even 6 feet if you want to be ultra safe, right? Keep the distance far enough away for where no one's going to be walking and just accidentally turning and looking at it, right? And then also, who's on top of the hospital, getting the stuff out of the drone, right? Is it, are these people knowledgeable about the system that they're going to be around so that they're trained? I mean, you think about, in the US, OSHA, right? We have OSHA requirements, and I go through OSHA training every year, right? And I'm just an office worker, right? I sit at my desk, I work on a computer, right? But I have to do OSHA training about all the things that are in my building, right? And so I kind of view it that way. That's another piece, right? Of, people who are going to be there are going to have to be trained to know that, hey, there is a laser on the roof, right? And you shouldn't be looking at it when you're less than 3 feet away from it. That should be part of the training package, right? So I think there's lots of ways to cover those kind of things.
Yeah, I think you'll find it's just to advertise them to the people that sign the checks, essentially.
That's right. Yeah.
Sorry, I've kind of dominating the conversation here. Any more points from the floor? Any things that you want to dig down in? No, I think we're good. I think you've covered everything. It's really exciting stuff. I mean, I'm an advocate of slow drones of all things. An airship blimp above a festival so you can deliver insulin, and the multiple drones being guided up and down seems absolutely fantastic for that point. And being able to do things in all sorts of weather conditions as well is essential to make sure that there's continuity in the logistics. But no, Gary, that was brilliant. So what I'm going to do now is I'm going to stop the recording. Oh, that's okay. Oh, hold on. Conrad's come back into the room. Conrad, before I start the recording, are you going to dive in with another question?
Just one more quick one. You touched on fog or weather or whatever. I'm thinking about this technology if there's an adversary trying to deliberately disable it. If I asked you as an engineer, how would you disable it? What is the sort of easiest way to make it not work?
You go through the standard, testing, that we've done, that we haven't really found anything that really essentially degrades the system to a point where it's not usable. Even some of the heavy rain that we've tested in, we've seen a 5% degradation on distance, right? So it's not really been a huge impact. I think, obviously anything where you could potentially block light, like, so if you actually went to the installation and could just block it, right, that'd be one thing. But from a distance, I think it becomes really difficult you can't spoof light, right? You're not gonna be able to spoof it. Even if you could provide a crossover grid. So this is something that we've actually looked at. So if you had two transmitting grids, right, overlaying the same point in space, right? We still, because the grids, like I said, they have encoded information in the grid lines. Part of the encoding is, which transmitter am I locked in on, right? So, for example, you could have on, like in the UAM space where we discussed this topic, you could have two transmitters on the vertiport, for example, for two different approach paths, and those approach paths could cross over each other, right? And if that's something that they wanted to do, and you would still, the aircraft would not get confused on approach and says, oh my God, I just saw another line, right, in another grid. I don't know where I am. It knows that I can ignore that because it's not something I know. I only know the grid. I chose the grid I want to be in, and I'm now locked into that grid. Now you can always change that grid as an option, as part of as a controller. But when you say this is the approach I'm taking, I'm in this grid, that's the one I'm taking. So I'm not really aware of any other technologies that I'm privy to, at least, where you can spoof or jam kind of a light source like a laser.
Yeah, that's right. Yeah, I think it sounds like quite a robust technology for sort of the approach phase of flight. Yeah, it's very interesting.
Yeah, so that's why we think it's an intriguing technology, because just it's, it's obviously its capability in weather. There's always RF type technologies, right, that you can use for things like this. Vision, you mentioned vision, right? I'm aware of who does those technologies, and I've talked to those companies, and we've talked about even collaborations, because we recognize not every system can solve every problem. Right. And so, and there's also, when you talk about safety, especially, when we talk about passengers on vehicles, right, you want to provide more redundancy and dissimilarity. And so one of the things, when you think about is, vision's great, and the technology works pretty well, right, to say, okay, I can see, here's my landing zone, I want to go land there, right, and I can find my way, without anything else to get down there, except for when I can't see. Right. So when I can't see, right, just like a pilot can't see, right, there's going to be certain minimums, right, where you can say, I can, just like today on today's aircraft, if I can't see it, I can't land at it. So
Yeah.
So the vision is good to a point, right? So when you think in the aviation space about like the Cat 1, Cat 2, Cat 3 type landings, right? The vision systems are probably never going to go beyond a Cat 1 landing at best, right? Where I believe a system like this could drive you and lead you to a Cat 3 approach, right? So I think there's opportunity there, right? Whereas, again, I'm not going to say that, the vision systems aren't great, because I think they're really cool and they work really well. But there are downsides to a vision system, and being able to see as part of fog, even in rain, right? How good are those vision systems in really bad, diverse conditions? And you can always say, well, I'm not going to fly in those conditions, right? Well, anyone that's flying for revenue service is going to be like, well, I want to fly in as many conditions as I can, right?
Yeah.
So, right, otherwise I'm not making money. So that's where we see things like this can augment other types of systems that are out there.
Yeah, that's right. That's key. It's the augmentation. I mean, a full navigation solution will always contain elements of different technologies if it wants to be robust. Yeah.
Yep.
Cool. Thank you.
Thanks, guys. I think that last part of the conversation, I think we need to get to our undergraduate engineers in their first year. That is absolutely a fantastic tutorial in safety. Really, really good. And just at a point, the view behind me is one of the rare days where it's sunny where I live. So trying to fly drones in the UK, it's not like Arizona or Phoenix. It's always raining.
I've been to the UK many times. We have well, you've talked to Richard, so I've been out by Richard many times. So when I see that out there, I'm like, wow, this is the one day I caught it.
Yeah, you run out. So Gary, thank you very much for a really good talk. It was really interesting, a lovely discussion, and thanks to Conrad as well. That's really good. So I'm now going to officially stop the recording if I can find that. Here we are.